Hello everyone. Our next discussion is on JK flip-flop. As we have seen in the previous video about the basic flip-flop, that is SR flip-flop. So we have seen that when all the four combination of inputs in SR flip-flop, when both are 0, when S is equal to 0, R is equal to 0, there will not be any change in the input. When S is equal to 0, the output goes to the set state. When S is equal to 0, output is 0. When S is equal to 1, output is goes to the set state. So depending upon the value of S and R, we can have the three combination of inputs in SR flip-flop. But we have one drawback in SR flip-flop, that if S is equal to 1 and R is equal to 1, we cannot use those inputs in case of SR flip-flop. Why? Because Q and Q bar will be having the same value when we start analyzing the SR flip-flop. But in order to overcome that condition, we are going for other flip-flop that is called as JK flip-flop. So JK flip-flop is similar to SR flip-flop with only small change. So JK flip-flop is also, instead of input S and R, we are having input as J and K, and same clock signal will be there, and the two outputs Q and Q bar, which are complement to each other. So now I'll write the logic diagram for JK flip-flop. You can see that it is almost similar to SR flip-flop. So I'll write here. Here also I'm realizing using NAND gate. This is clock. This was S and this was R. So instead of that, I will write this is J and this is K. So here the output is Q and the output is Q bar. This is similar to your SR flip-flop. The only change which I have to make in SR flip-flop in order to make use of the condition S is equal to 1 and R is equal to 1 is, I will be taking the feedback from the output S. This feedback I will take from Q bar and I will give it as input for this NAND gate, and I will take the feedback from Q and I will give it to input K. So this is the logic diagram for JK flip-flop. It is similar. It is similar to SR flip-flop. The only thing is you will be having a feedback from Q and Q bar to J and K. So let me analyze it for all the cases. So I'll write the truth table for JK flip-flop here. J, K, and the outputs are Q and Q bar. Here one more input is clock. I will be assuming that for all the combination here J is equal to 0, 0, 0, 1, 1, 0 and 1, 1. So this is the combination of inputs. So this condition I'll come in the next step. So first I'll take J is equal to 0 and K is equal to 1. Here also, since I am using the NAND gate, I will write the truth table of NAND gate here. NAND gate is nothing but negation of AND gate. AND gate is high only in this condition. So NAND gate will be 0 only in this condition. For all other values, the NAND gate output is high. So that means if any 1 0 is zero is there in any of the input, your output is high. Okay. So first condition I will take, clock is 1. Write this in properly. From Q bar from Q, the output is given to K. Okay. So first condition I'll take, J is equal to 0 and K is equal to 1. When J is equal to 0, K is equal to 1, clock is equal to 1. When J is equal to 0, irrespective of other input, the output is high for NAND gate. When this is high, I cannot predict the output of this NAND gate without knowing the input. So let me take, I will assume, because since both inputs are high here, I cannot get the output of this state also. I cannot get the output of this NAND gate also. So let me assume Q is 0 and Q bar was 1 in the previous output. When it is 0, this 0 will be, so when this is 0, the feedback you have, say I have taken the feedback from Q to K. So that means this will be 0. Just a minute. This will be 0. So output is high here. So now when Q bar is equal to 1, the output is 1. Q is equal to 0. Here output is 0. So 1 and 1, the output of next state will be 1 and 1. The output will be, when both are 1, the output is 0. So next output of Q bar is 0. Here 1 and 0, the output is high. That means when J is equal to 0, K is equal to 1, output is 0 and 1. Similarly, when J is equal to 1, you can analyze it. When J is equal to 1, K is equal to 0, your output will be 1 and 0. When both are 0, your output will be no change state or the memory state. Now, let me analyze these values. This is the most important combination of inputs which we will be using in counters. So we will be using this condition whenever I'm designing the counter. So for counters, we will be using JK flip-flop. So let me take this condition and discuss each output in each and every step. Now my condition is J is equal to 1 and K is equal to 1. Clock is also 1. I cannot predict the output of both the flip-flop because both the conditions are 1 and 0 is not present in any of the input terminals. So what I'll do, I will assume Q is equal to 0 and Q bar is equal to 1. You can assume either condition also. You can assume Q is equal to 1 and Q bar is equal to 0. So first time let me assume that Q is equal to 0 and Q bar is equal to 1. So this is nothing but the previous state. Let me take Q is equal to 0 and Q bar is equal to 1. So when Q is equal to 0, this is given or fed back to K. This is given to first flip-flop. So 1, 1, 1. When all are 1, the output of NAND gate is 0. When any of the one input is 0, the output of this NAND gate will be high. So next, this 1, so this there is a connection here. So when input to this flip-flop is 0, irrespective of other input, your output will be high. You make a note of this. High is very important. So this high is given as a input for this flip-flop. So 1 and 1, your output will be 0. Here you will get 1 because this 1 output is fed back to this NAND gate. So your output will be 0. Now just observe the output. Whenever your previous condition was 0, your next state is 1. Whenever your So that is nothing but whenever you are having out previous state is 0, you will get it as 1. Now I will assume, see now you have the condition. What is the present output now? Now the present output Q is equal to 1, Q bar is equal to 0. Let me take this as the previous input and I'll check what will be the output of next state. Okay. See, input will be same. J is equal to 1, K is equal to 1. So instead of 1 is, see here, Q bar is 0. So this 0 will come here. Q is equal to 1. This 1 will come here. 1, 0, 1. Output is high. 1, 1, 1. Output is 0. So irrespective of other input, the output of this NAND gate will be 1 because 0 is one of the input to this NAND gate. So your output is high. So this high is given to this NAND gate. 1 and 1, your output will be 0. So keep observing these values. When previous state is 0, next state is 1, next state is 0. Once again you take this, you will get 1, 0, 1. So that means your output is toggling. So it is toggling between the two states 0 and 1. So that means you can make use of this input. So this is nothing but toggling. Whereas in case of SR flip-flop, we cannot make use of these two flip-flop because Q and Q bar were same. But here you can make use of this combination of input for designing counters and other circuits because I am getting some output which is toggling. Okay. I hope you understand the truth table with different combination of inputs. Thank you.